So we've looked at how the individual units are arranged in a crystalline solid, but we can also divide crystalline solids by what those individual particles are. And so this is kind of an overview of what we're going to talk about. So crystalline solids, we can divide these into molecular solids, ionic solids, and atomic solids. And then the atomic solids are further divided into three categories. So a molecular solid, as the name suggests, is a solid where the units, the individual units, are molecules. And so examples of this would be ice, which is solid water, and dry ice, which is solid carbon dioxide. So the individual units are not atoms or ions, but molecules. The molecules are held together by intermolecular forces. And because intermolecular forces are fairly weak, molecular solids tend to have low melting points. In an ionic solid, the composite units are ions. So you've got cations and anions. An example would be table salt, sodium chloride. Here, the ions are held together by coulombic interactions between cations and anions. Those are ionic bonds, electrostatic attractions between opposite charges. How do ionic bonds compare to intermolecular forces in terms of strength?
Stronger.
They're much stronger. And so because of this strong interaction that's holding the particles together, ionic solids tend to have high melting points. Some of them are extremely high. The coordination number, remember that's how many other ions an ion is directly touching, represents the number of close cation-anion interactions. Those close cation-anion interactions lower the potential energy. And so there's a bunch of different factors that together decide what sort of a packing structure an ionic solid is going to have. We've got balancing of coordination number. You have to have charge neutrality, and then you have different ion sizes, and so that complicates things as well. When the cations and anions are similar in size, that makes things a little easier. Here, cesium chloride, cesium ions, cations, and chloride anions are similar in size. And so these are going to pack together in a simple cubic structure with cesium ions in the center. We've got a coordination number of 8. And each of these unit cells is going to have one of each ion, one cation and one anion. Calcium sulfide has the same structure. Calcium sulfide is calcium 2+ ions and sulfide ions. So again, we have a 1-to-1 ratio of cation to anion, and those two ions are similar in size. So they can pack together in this way. Some ionic solids have ions that are very different in size, like sodium chloride. The sodium ion is much smaller than the chloride ion. So because of this, it imposes some limits on the structure. We have to have one cation for every one anion. So we have to have charge neutrality, but our coordination number is limited to 6. It can't do 8. Rock salt, this is an example of rock salt, which is there are different forms of sodium chloride. This has a face-centered cubic structure with sodium ions between, and that's missing. Hang on. The sodium ions are between the chloride ions. So chloride, sodium chloride, sodium chloride. The chloride, though, is, we see here, this is the face-centered cubic structure, right? Here's the face. And then the sodium ions go in between those. So each of these unit cells has 4 of each ion, 4 cations and 4 anions. Other compounds that do this are listed down here. And they're going to form this structure because they have equal charges on the cation and the anion, and one of the ions is significantly smaller than the other. If we get an even larger ion size difference, we can get something like this. Zinc sulfide, many ionic compounds can form different crystalline structures. and that affects their appearance macroscopically. This is called zinc blend, zinc sulfide, and here we have sulfide ions in a face-centered cubic, and the zinc ions are in half of the tetrahedral holes. Like, what the heck is a tetrahedral hole? Well, if you look at this zinc ion, maybe this one, it is in direct contact with 4 sulfide ions. So if we were looking at covalent bonds, we'd say the zinc is tetrahedral in shape because it has 4 bonds. Only half the holes, though, have zinc ions, because if they all had them, we wouldn't have charge neutrality. So again, in this cell, we have 4 of each ion. And this is an illustration of that tetrahedral hole. It's a hole between 4 of the other ion. Lots of solids, ionic compounds, have unequal numbers of cations and anions because the charges are not the same. So here's calcium fluoride, CaF2. There's twice as many fluorine ions as there are calcium ions. So fluorite has a calcium ion in the face-centered cubic structure, and here fluoride ions are in all of the tetrahedral holes. So the tetrahedral holes formed between the calciums are all filled with fluoride, whereas in the previous example, only half of them are full. So here, a unit cell is going to have 4 cations and 8 anions. So that's one structure. There's also an antifluorite structure. And here's an example of some other compounds that take on this shape. Atomic solids, again, the name is suggestive. The individual particles in an atomic solid are atoms. And then we divide these atomic solids based on what's holding the atoms together. Non-bonding atomic solids are not held by bonds of any kind. They're held together by weak dispersion forces. Atoms only have dispersion forces. An atom can't be polar, and so you can't have dipole-dipole forces or hydrogen bonding. They're going to form the closest packed structure to maximize the coordination number and minimize distance in between them. Because these are held together by dispersion forces, they have very low melting points. Those melting points increase with molar mass. The only examples of these types of compounds, solids, are the noble gases in their solid form. And you have to get to a very, very low temperature to solidify those noble gases. Metallic atomic solids are held together by metallic bonds. We kind of have talked about those a couple of times. That's the electron C model, where the valence electrons are free to move around inside the metal, and that holds the metal together. These are also going to form closest packed structures. The melting points of metals vary. Some of them are very high, some of them are quite low. We know that mercury is a liquid at room temperature. Gallium melts in your hand. It has a very low melting point, but others have extremely high melting points. And so here we have examples of nickel and of zinc. And the individual atoms are held together by metallic bonds. And then we have what are called network covalent atomic solids. In these molecular compounds, well, I'm sorry, they're not molecular compounds. In these substances, which are elements, instead of the individual atoms being held together by dispersion forces, they're actually covalently bonded to each other. And so this is kind of an odd situation. So diamond is pure carbon, and graphite is pure carbon. And they are both covalent network solids, or network covalent solids. The difference is exactly how the bonding occurs. In graphite, we get these hexagonal rings of carbon, and they form layers. So we have a layer of carbon atoms that are covalently bonded to each other, and then we have another layer. The next layer is held to the first layer just by dispersion forces. And so graphite is slippery. If you're writing with a pencil, that's mostly graphite in the lead of your pencil. It's slippery and will rub off because it can separate those layers very easily. A diamond, on the other hand, has covalent bonds in a three-dimensional structure, and because it's all held together by covalent bonds, it's very strong. A diamond is a giant molecule. Yep, a giant molecule. These are not going to form the closest packed structures because they're not just a collection of spheres that are piled together in a box, like we've been thinking of. They are bonded, and so it depends on the geometry of the bond. It depends on the hybridization of the orbitals, etc. Silicates are also considered atomic solids because they do not contain discrete molecules. Okay, a silicate is silicon and oxygen, and it's usually 2 oxygens to every silicon atom. The reason it's not a molecular solid is because the silicon and oxygen atoms are covalently bonded to each other. There are no individual molecules that are held together by intermolecular forces. And the way that these are bonded together can vary. And so if you see, I think quartz is a version of silicate that's very regular in its structure. Glass is also a silicate, but it's amorphous. And so it's just kind of randomly bonded together, and so it doesn't have the crystalline structure. But these silicates have high melting points. So sand is mostly silicate. So any questions?